Good day, mate. This is Hamak Lee, your Quantum Odyssey tour guide. And today, I do have like a small update regarding the format of the upcoming videos because I have catched up on days 4, 5, and 6, which are otherwise reserved for my hackathon, which I did not win. But after reviewing these, I realized that first, maybe the time that it was like uploaded wasn't the most ideal. Like I have uploaded this all the way in like 4 a.m. UTC, so it might not be like peak time over there. And secondly, I realized that these videos are often like 20 to 30 minutes long, so that would mean like a lot of rehearsals, and I want these sessions to like run smooth because the initial sessions, pilot sessions, did not go too smooth. Although it did like get like a considerable amount of traffic. Unfortunately, this wasn't really the case for the most recent ones. So here are a few updates I can give to you. The first is this. I'm going to set up a poll on Discord to see like, would you like to prefer long sessions or would you like to prefer short sessions? So session length. Session length. And the other one is I'm actually going to remake the last week's day on Easter Monday and possibly Easter as well, which will be much more rehearsed than the original because like rehearsals could definitely like increase the time spent on making these videos as much as 3 times 4 times longer, and this is ultimately like a side hustle for me. I want you to be able to digest my videos just like the Khan Academy videos as well, but sometimes it does get a little bit like too long. I do not want to stretch this thing too long, so if the session length is the long one, I would dedicate at most 10 seconds, 10 minutes on explaining the basics of the gate, and then maybe like another 20 minutes to explain how these gates, the applications of these gates, like simple combinations of these gates and sample problems that might be I've either made up or already present on Quantum Odyssey. Today we will do an S gate and a Y gate together. So this is really the official day 9, but again, the S and the Y gate, everything will be remade. Everything will be remade. And if you're curious, I'm actually recording this using a combination of OBS and Zoom. I'm not sure like if you also prefer like something like a live stream or something, but hopefully like the live stream version, which is really like the final rehearsal, might also work. So what is the S gate? The S gate is another phase gate. That applies on a qubit. That means a binary digit on its lane number. It says this. At advance phase by 90 degrees, that means pi half, if the applicable qubit is at 1. This is the S gate. We will explain how the S gate works in a more visual way. So let's say we have a single gate. So an S gate causes a blue qubit sigil on the left lane to remain blue, but a blue sigil on the right lane to turn green. There is a period warp cycle, so a blue qubit undergoing a green transition would turn green, then it would turn red, then it would turn golden. So this is what the S gate does. Two sigils at one place. So sigil at qubit k. Additionally, if you apply four S's in a row, of course, so 4 S's in a row, so this is going to be the diagram, 4 S's in a row, it would equate to the identity gate again. So let's say 2 sigils, the left one would stay blue throughout, but the right one would cycle from green, that means imaginary, red, that is negative, yellow, that is negative imaginary, the other square root of -1, and finally blue, and so on. So let's going to draw this. 0 plus 1. Let's write it better like alpha 0 plus beta 1. Alpha 0 plus I beta 1. Alpha 0 minus beta 1. Alpha 0 minus I beta 1. Alpha 0 plus beta 1. This is let's say this is going to be state psi. After applying the S gate, it's S of psi, then it becomes Z of psi, then it becomes S dagger of psi called S adjoint of psi, and finally I of psi. From there it is evident that SS equates to Z. Then we have S cubed is equal to ZS and is equal to SZ. So they commute. It's as if there is like a group theory term, let's say like S is a centralizer of Z and Z is a centralizer of S. Basically, centralizer of a group element means all the group elements that commutes with that group element. So it's a bit conditional. Center is like the abelian parts of the group. So it's basically the subgroup which is completely commutes with every other element within the subgroup. And finally, S quartic is just equal to I. We also know that S cubed is going to be equal to S dagger, and finally S dagger is equal to S dagger S is equal to I. The dagger is somewhat like an inverse. We will explain more about the daggers operations after we go on to the mathematical part of this. But just right now, you can take the dagger as the operation that undoes the base operation. But if I want to break it to you right now, you can say that all the gates we have gone through are called unitary gates. The explanation of a unitary gate is just very simple. It's just like the gate that is equal to its own adjoint. But what is an adjoint? That would mean express this in terms of a matrix, but it involves transposing and conjugating. Let's try a multi-qubit case of the S8. So let's try a 3-qubit case. So we will start with 3 qubits. Now let's apply an S gate on the 0th qubit. So that means each of the 8 lanes will be divided into 4 pairs of adjacent lanes, and the right lane of each pair would be made green. Now let's apply the S gate on the 1st qubit. That means the pattern would be 2 blues and 2 green wires. And finally, let's produce a Z gate on the 2nd qubit. That means the wires will be divided into 2 halves. The right half would be green. Okay, so in the circuit diagram, it will look like this. So it's going to be S, S, and S. This is actually equivalent to a parallel application of 3 S's. Let's say that there are 8 sigils, all blue and all falling down on the circuit. So any ball whose lane on the lane number with exactly 1 applicable qubit being 1 would be affected by the S gate once. So it would be green. These are 0, 0, 1, 0, 1, 0, and 1, 0, 0. Likewise, any qubit sigil on a lane with 2 bits at 1 would be red. So we have 0, 1, 1, that's number 3. We have 5. We have 6. And finally, the last one would be yellow. That means all 3 would be at 1. So likewise, we have the leftmost sigil being unaffected. And you can also make a pattern like that. So start with blue, green, green, red. And then if you add an S on the second qubit, the entire right half would be as if they've all been applied an extra state, turning into green, red, red, yellow. Let's try another example this time. So of course, we have XS and SXX and XX to make a Y gate. So S dagger, S dagger, so X, then S over there. So we have S dagger, X, and S. What does it do to like a blue sigil on the left? The blue sigil on the left would turn green as well. So it would switch space, and then it would also be like separated from together to apart. So now let's try the sigil on the right. So blue turns yellow and then switches spots. Okay. This makes up the Y gate, actually. The Y gate can be summarized as doing like an X and an S, like a Z all in one. Because the S part is it creates qubits whose sigils are pointed in the imaginary direction. The Z part is now the qubits have the opposite sign, and the X part is that the qubits have also switched, especially if the qubits are unequal in size. So this makes up the Y gate. The Y gate is the last of the gates to be introduced, and in Quantum Odyssey it's surprisingly short. So this is the Y gate. It also does the cross, but it also changes the color from the same to the opposite. And like all the other polygates, it is its own inverse. So let's draw another green and a yellow. So a yellow that faces a green would go back to blue, and the green that faces the yellow will go back to blue. Because S and S dagger makes up into I. It's like this. Let's say we have two arrows. Being applied a Y gate. Now the arrows face the opposite direction now, and they also switch spots. And finally this blunt head, when applied an X, S would turn clockwise and turn back into a sharp arrow. Sharp would turn counterclockwise and turn blunt. So let's do this again. So this is another way to visualize a Y gate. Let's examine what happens if you perform parallel Y gates. So here's the answer. So let's try a Y on the first qubit and the zeroth qubit together. Okay, so a sigil at 0, 0 would encounter two greens in a row, so it would become red. 0, 1 would become blue again. Then 1, 0 would become blue, so they cancel out. And 1, 1 would become red again. So the number of turns would be number of turns anti-clockwise is the net difference between the zeros and ones on the qubit identifying the qubit string identifying the lane. So this is the combined circuit for a Y on both qubits. So you can create this without using any entanglement. Now let's say what happens if you perform a Hadamard on that combination. So now the pairs are identified by blue and red, but the left pair, however, it's red and blue in this order. So let's apply an H there. Okay. So let's analyze this. Red blue. Red blue is just the negative of blue red. And when the qubits have opposite signs, the sigils have opposite signs, when applied to an H, it combines into the right lane. So in this case, the left lane would be nullified because it's blue and red combined. So it cancels out. The last one would be this. Red and red over there, which becomes a full-sized red qubit. Red sigil. Remember like last time when you're performing a Hadamard on a blue and red? That's just the effect of performing a Hadamard on a blue qubit on the right. This relationship can better be explained in terms of basis, because the H gate can be said to transform a qubit measured in the default basis, also called the Z basis, into the X basis. And the Hadamard is basically the bit flip on the X basis. The S and S daggers are like the bit flips in the Y basis. Let's try again with 3 qubits. So now we have this. X gate on the 0th qubit, Y gate. Now Y gate on the first qubit. So crisscross with 2 at a time. Now finally a Y on the second qubit. That means 4 at a time. So let's write this down. Now let's see how the balls roll. So 0, 0, 0 would have 3 zeros. That means translates to 3 greens. That would be yellow. 0, 0, 1 would have a net of 1 green, so it's green. Likewise, the same goes for 0, 1, 0. So 0, 1, 0 would be green. Finally, we have 0, 1, 1. That will be 1 yellow. Likewise, on the right half will be transported to the left half, and the orderings will be reversed. So it's for 1, 0, 0, it will be green, green, yellow. The 1 on the left is being corresponds to the yellow. Now we have 101, 101. So that's a palindrome. And 110, so 0, that's 0 qubit 1, 1, 1, 0, so yellow. Then finally 111. So that's like this. 3, 6, 9. That's divided by 4. That would leave a remainder of 1, so it's going to be green. So here is an observation. can say. So a parallel application of the Y-gate yields results in green and yellow for odd number of qubits and blue-red for even number of qubits. The last question is, when should you use a Y-gate? When should you use a Y-gate? Of course you want to switch. You also want to deal with clearing sigils which have the green and yellows, as well as to make the sigils with the same sign to opposite signs. That's when you should use the Y-gate. You should also use the Y-gate if you think like you can express it like more succinctly than just using X and Z together. Finally, let's explain about the Y basis. So here is an example of the term basis in action. So we have, let's say we have some states. Z of 0 is equal to 0. So this is equivalent to blue and red. Likewise, Z of 1 is just equal to like a scalar multiple of 1. It does not change the sigils positions. It only or sizes. It only changes the colors. So we have this. We say that the Z gate that Z that 0 and 1 are eigenstates of the Z gate or Z operator. Likewise, we have the X. So X, applying an X to the plus state still yields the plus state. That means if you switch to identical objects, it would still be the same. So please remember a qubit, or isolating like individual qubit, is equivalent to like a pair of circuits. Likewise, we have X of the minus state is equal to the minus state. Minus means blue, red. Which just turns into red, blue. Which is just simply the minus state. Likewise, it also works on this. So X then minus plus is still equal to minus plus. So it's like red, red, if you switch together, would still be red, red. Likewise, we have green, green switch together, so any scalar multiple of that would still be an eigenket. Of of these two measurements. That means like measuring the x basis. Basically, the z can be converted to the x basis using the Hadamard gate, because it converts 0 into plus and 1 into minus, and backed because the Hadamard gate is its own adjoint. Let's examine the y gate, the y basis, because this might help you on breaking down certain problems when there are more complex amplitudes. So let's consider the circuit that's being operated by S. So that will be blue-green. So this is like an S-like combination. That means the two sigils are 90 degrees in terms of direction. Blue, yellow. In this case, the green which meets a yellow becomes back into blue, and the blue that meets green becomes green. So this state is called the right state. The right state. Likewise, blue and yellow is called the left state. So, and then apply a y gate on there. So in this case, yellow with yellow mean like 6 S's. That's the same as 2 S's, because 6 is 2 mod 4, so it's red. And blue becomes green. In this case, we end up with this. We have the left state, the backward state being applied with the y will become the negative of the left state. You can identify this like right state. So the will be this. This is right state. This is left state. Left-handed, right-handed. X1, X2. Right-handed coordinate system, left-handed coordinate system. There are also 8 other pairs of sigils of 2 colors which are quarter of a turn apart. Namely, these are just we have the I copies of the left state, right state, negative I or negative of left and right. Therefore, we conclude that S of 0 is equal to the right state, and S of 1 creates the left. Likewise, S of, let's say this. What happens if you apply we can conclude that H S of 0 is the right state. Likewise, we have H S of 1 to be the left state. So applying an HS converts qubit in the Z state H then S into the Y state, the Y basis. And how do you invert that? To invert that, you first combine, you perform the opposite operations. So likewise, we have S stagger of the right state S stagger, and then plus an H to convert eigenbasis in the Y state to an eigenbasis in the Z state. Also, like in short, we can therefore do the statement over there. So Z gate applied with an H. So H transforms the qubit that is in the Z eigen of the Z states basis into that of an X. So it's going to be 0 and 1 becomes plus and minus. Plus and minus, we perform an S, and then S stagger to transform it into the Y state. So let's draw this again. Circuit that converts Z basis qubit into Y basis qubit. So converts that into this. So blue will be split into blue-green, and blue on the right would be split into blue-yellow. And likewise, let's do the S stagger and S and H. So we have this blue, then yellow, yellow. So it will be blue will remain blue, so blue over there, yellow, and green. So these two gates are the gates which transforms Z into 0 and 1 into left, right, and left. We will use the Y gate frequently on puzzles which require like optimizing the number of gates. In terms of like number in both dimensions, that means the depth of the gate and the overall number of the gates used, including control operators. Like and subscribe to my channel again, and please remember that the format and everything will be revamped. Every first ring material will be revamped. Next week, we'll focus on solving certain challenge problems and using what we have learned on the previous set of videos.